Hello, welcome to our channel. In this video, we are going to build a 6 degrees of freedom robot arm from mostly 3D printed parts. We'll be going over the process of building the robot, the challenges we faced, and how we overcame them. Before we get started, let's outline some of the goals we want to achieve. It should be visually appealing. It should be able to carry at least 500 grams so we can mount like a phone to it or something. It should also cost about $700. To start designing our robot, let's take a moment to understand how the robot's controller works. It takes a point and orientation in cardinal space as an input, and then it performs some calculations based on this input. After the calculations, it outputs the joint angles the robot needs to reach that point. But the question is, how are the joint angles calculated? Here's where inverse kinematics come in. There are various methods to solve inverse kinematics, such as numerical, algebraic, and geometric methods. But because of how complex the 6DOF robot is, the algebraic and numerical methods won't be feasible. So we have to use the geometric method. Let's take a look at how the geometric method works. We assume the first 3 joint angles determine the position of the end effector, and the last 3 joint angles determine its orientation. And so using trigonometry and vectors, we find the first 3 joint angles. Then using those angles, we can find the last 3 joint angles. I have linked an article in the description that goes into detail on how this is done. Now that we know the angles each joint should move to, the next step is making sure all the motors reach their target angles at the same time. The Excel stepper library has a class for controlling multiple motors together, but it doesn't support acceleration or deceleration. While this works at low speeds, stepper motors can't jump straight to high speeds without ramping up, so we are going to build our own algorithm to handle acceleration and deceleration smoothly. Here's how the algorithm works. We start by identifying the stepper motor that needs to rotate the largest angle. This motor becomes our reference or independence variable. Next, we calculate how much each of the other motors need to move in proportion to the reference motor. As the reference motor moves one step, the other motors take steps based on their calculated ratios. This keeps the motors synchronized so that they reach their target positions at the same time. Motor speed is controlled by adjusting the time delay between each step. A shorter delay means faster movement, while a longer delay slows it down. Using this principle, we can create acceleration and deceleration by gradually changing the time delay. By progressively decreasing the time delay, the motor accelerates, and increasing the delay causes deceleration. To calculate the exact delays needed, we use Hilbert equations. These equations allow us to relate the motor's position to time, giving us precise control over speed and acceleration. Now that the algorithm is sorted, let's talk about the mechanical design. We'll be using 5 NEMA 17 stepper motors and 1 NEMA 23 stepper motor. For joint 1, we are attaching a 50:1 planetary gearbox to a NEMA 17 and then driving the joint with a 3:1 pulley. This gives us a total reduction of 150:1. Joint 2 requires a lot more torque since it is carrying the whole arm. So we are using a NEMA 23 paired with a 50:1 planetary gearbox to directly drive the joint. For joint 3, we'll mount a NEMA 17 with a 50:1 planetary gearbox and use a pulley with no reduction to drive the joint. For joints 4, 5, and 6, we are using NEMA 17 motors that already came with 5.18:1 planetary gearboxes. Joints 4 and 6 will be driven directly, while joint 5 will use an additional 3:1 pulley, bringing the total reduction to approximately 15:1. With all the mechanical components in place, the next step is assembly. We ran into a bit of a problem. The rods didn't fit into the other parts because they were designed to be angled slightly towards each other. This meant the rods needed to be inserted into both parts at the same time. However, we first inserted the rods into one part, and when we tried to add the other, it didn't fit. Since removing the rods was difficult, we had to destroy the parts and print new ones. We've taken out the rods and printed new parts, so we can continue with the build.
Is that your phone?
Yeah, that's it.
Yes.
That sound you are hearing is the belt on joint 3 slipping, which means it can't handle the weight of the second part of the arm. We are not entirely sure what's causing this, but we suspect the support for joint 3's motor is weak, causing it to bend when we try to tension the belt. To fix this, we'll redesign the arm with stronger supports. But before disassembling the robot, we'll home the other joints to ensure they are working properly. Unfortunately, we couldn't home joint 2 because unplugging the microcontroller caused erratic movement, which ended up breaking the limit switch. In addition to reinforcing the supports, we've decided to replace the NEMA 17 stepper motor with a NEMA 23. This ensures the motor strength won't be an issue anymore. Now that all the changes have been made, we can retest joint 3.
The sound is making us. Yeah, where's the sound from? Is it the stepper motor? Yes. Put around into open mode.
Even after tensioning the belt again, the belt tension still wasn't strong enough, and so it started slipping again. We are going to have to take the robot apart and adjust the tension one more time.
Is it the motor that's doing that or what?
While the belt tension isn't as strong as we would like it to be, it's good enough for now. We can finally move on to testing the inverse kinematics code.
Oh, it's just straight in now. I think to be fine, I don't know. look at it. This thing's working. I used it. Noir. Bra. Yeah, noir, bra. I'll take it. I cut a band there. I change wire. Take it to the side. You change around.
As you can see, there's still a lot of work to do. The shaft holding the second part of the arm failed because of the tension in the belt. Tensioning the belt has been a real challenge, so we've decided we are going to mount the motor directly to the joint. This change will also help reduce backlash and minimize jitter during movement. Another improvement we'll make is fixing the limit switch placement for joint 2. Right now, it's too fragile and breaks easily. We are considering switching to a proximity sensor instead, as it doesn't require direct contact, so it will be more reliable. If you enjoyed the video, please give it a like, and don't forget to subscribe if you'd like to follow along as we continue building this robot.